Okay, good morning, everyone. Today I'm going to present my topic on triple integration, integral, and uh, applications to the mass and density problems. So, in these presentations, I will mainly focus what triple integrations are and how they works in three-dimensional space and how they applied in practical situations like finding mass, center of mass, and moment of inertia. So let's begin. First of all, what is triple integrals? Okay, before understanding triple integrals, let us remember what we already know. That is, we know that a single integrals is used in one dimensional, and double integration. Double integrations extends these ideas into uh, two dimensionals. Similarly, triple integrations extends the concept into three dimensionals. So, in simple word, in simply, we can say that triple integral is used to integrate the functions uh, f x y z over the three dimensional regions. Uh, so triple integrations extends the concept. So here, integrals extends the concept of double integrations into three dimensional. Instead of working only with the x and y, now we include z also. So we are working in three dimensionals space. So in second point, if the functions f x y z equals to 1, then the triple integrals gives us the volume of solid regions. So but if we use density functions represented by rho, here it is written as rho, a function of rho xyz, then triple integrals gives the total mass of the object. So the third point is three dimensionals. In triple integrals actually are useful because they helps us analyze and different physical quantities like mass, density, and center of mass, and likewise moment of inertia. So basically, triple integrals helps us students real life and three-dimensional object. Now, defining the volumes and triple integrals first. Now, let's see how triple integrals are defined. In multi-calculus, triple integrals extend single and double integrals into three dimensions. So, the idea is based on accumulations. Suppose we have a solid regions called E, and we divide this large solid into many very tiny rectangular boxes. Each tiny boxes has a small volume represented by delta V. So now what we do is we find the volume of a functions at each small box and multiply it by its volumes. Then we add all these values together. This process creates uh, what is called that Raymond sum. So as the boxes become the smaller and smaller, the approaching zero sizes, then the summations approaches the exact value of the integrals. That's limits becomes our triple integrals. So simply, triple integrals are just adding in infinitely many tiny volumes together. And now we comes to coordinate systems. Here, different coordinate systems helps us solve problems more easily depending on the shape of the object. There are many three coordinate systems. First is Cartesian coordinate systems. In coordinate systems, we use x, y, z values directly. This systems is mostly used for rectangular shapes or box-like regions, so to say. And in second is cylindrical coordinates systems. This systems is useful for objects having circular symmetry around an axis, for example, cylinders and cones. And third is what is called that spherical coordinate systems. These systems is useful for spherical objects such as spheres and hemispheres. So instead of using different equations in Cartesian forms, changing coordinates often makes circulations much easier. This style sounds like the students actually what is called that uh, uh, what is called that in spherically this uh, sounds like the we are making the calculations much easier uh, by changing the coordinates often makes the calculation much easier. And in next slides for calculating the mass, now let's move to an important applications of trivial integrals, which is calculating mass. And suppose an angle occupies a solid region called E and density is not constant throughout the objects. If the object is constant, then finding mass is very simple. We can just use mass equal to density into the formula. But in real life, density often changes from one point to another. So in that situations, we cannot use this simple formula. Instead, we use the density functions represented by the written as rho xyz functions rho xyz. To find the total value, we integrate these density functions over the entire regions using triple integral. So mathematically, we can say mass equals triple integral of density over the whole regions. So what this really means that we divide the object into many tiny pieces, calculate the mass of each small pieces, and then add all them together. In next slide, center of mass. Now let's understand the center of mass. The center of mass is simply the balance point of an object. We present it by coordinates x bar and y bar and z bar. So if we think about the balancing or rulers on our hand, there is one point where the ruler balance perfectly. That point is of center of mass. And now to find the center of mass, first we calculate something called moments tells us how the mass is distributed around the coordinates planes. There are three moments, that is m y z, which is the moment about the y z planes, and m x z means which is moment about the x y z. After calculating these moments, find them by totaling total mass. So x bar equals to myz divides by m, so on. Similarly, z bar equal to x what is called that m xy divided by m. So simply we can say that center of mass tells us the where the object is balanced according to how the mass is distributed around it. And in a moment of inertia, now let's discuss about it. A moment of inertia measures how difficult it is to rotate an object. We can call it resistance to rotations. For example, it is easier to rotate a small wheel than a large heavy wheel. So this happens because of moment of inertia. Moment of inertia depends on two things. First is mass of objects, and second is how far the object is from the axis of rotations. So if the mass is farther away from the axis, then more force is needed for rotations. Mathematically, we calculate it by integrating the square of distance from the axis multiplied by density. For example, the rotations about the z-axis, here distance is squared becomes x squared plus y squared. So large distance means large moment of inertia. And again, defining and notations. So uh, now let's see the mathematical definitions of triple integrals. So suppose f is the continuous functions over the solid region E. We divide it E into the many small boxes, as we talked before. So this process is represented mathematically using limits. Now another important concept here is Fibonacci theorem. Fibonacci theorem tells us that for the continuous functions, we can change the order of integrations. And for example, we for example dx, dy, and dz, or dy, dz, or dx. Any order can used if it is makes the problem easier. So Fibonacci theorem gives the flexibility in solving the problems. And next slide, cylindrical and spherical coordinates. Now let's discuss the cylindrical and spherical coordinates. Some things solving problem in Cartesian coordinates becomes difficult. So we change the coordinates according to the shapes. First is cylindrical coordinates. Uh, trans the transformations are x equals r cos theta and y equals r sin theta, and z remains z. This coordinate systems is useful for what is called that cylinders, cones, and circular object. The volume elements becomes del V equals r dz and dr and j theta. The extra terms r becomes from the Jacobian. Now let us see the spherical coordinates. The transformation are x equals rho sine phi cos theta, and y equals rho sine phi sine theta, and z equals rho cos phi. This coordinate systems is useful for the spheres and another hemisphere. The volume elements show here. The volume elements becomes dv equals del v equals rho squared sine phi and d rho d phi d theta. So again, the extra terms comes from the Jacobian. So changing coordinates makes a complicated calculations easier. And in next slides, physical applications mass from the density functions. Now let's see the physical applications of the mass from the density functions. Density functions represents the mass for unit volumes, and units can be kilogram per meter cubes and gram per centimeter cubes. And the formula of mass is mass equals to m equal to triple integral of density over the regions E. And now let's see some special cases. For first case is if the density is constant, then mass equals densities multiplied by volume. So in second case, if rho equals k times x squared plus y squared plus z squared, then uh, sorry, then density increase as distance from origins is increases. In third case, if rho rho equals in kz, then density increase with height. Now there are four steps for solving the mass problems. The more first model the objects, and second define density, and then third set of the integrals, fourth is evaluating the integrals. So these are the general steps we follow. And in next slides, about now let's discuss about the center of mass in more details. And so yeah, the center of mass is the point where total mass can be concentrated, as we discussed before. First, we calculate the moments about YZ planes, and similarly moment about the XZ planes, and similarly XY plane. After calculating the moment, we find the coordinates of the center of mass, that is x bar equals to myz divides by m. Similarly, z bar equals to mxy divides by m. One important thing is centroids and the center of mass. If density remains the constant throughout the object, then center of mass and centroids becomes the same. Mm, let's us discuss about the solving. Here is the solving and examples. We need to find the mass of the tetrahedron bound by x equals to 0, y equals to 0, and z equal to 0, and x plus y plus z equals 1. Density is given as rho equals xyz. Step 1 is identifying the regions E. We first understand the boundaries of the solid regions. Step 2 is setting of the integrals. So we write the limits according to boundaries. Step 3 is integrating with the with respect to z first. After that, we integrate with respect to y and then x. After completing all calculations, we get a mass equals 1 divided by 700 22. Approximately this becomes 0.001389. So this is the final mass of the tetrahedrons. And this is another worked examples, center of mass of hemispheres. So similarly, we can see here the calculations. This gives the balance point of the hemispheres. And at last, key points. Now let's us summarize the presentation. First, triple integrals extends the what is called that uh, extends integrations into the three-dimensional shapes. And second, mass can be calculated by integrating density functions. Third, center of mass uses moment divided by total mass. Fourth, moment of inertia measures resistance to rotational moment. Finally, changing coordinate systems such as cylindrical and spherical coordinates help simply difficult calculations. So overall, triple integrals are powerful tools because they connect uh, mathematics with the real world physical problems. Thank you. Only this much today. I would like to stop my presentation now. Thank you, everyone.